So, we have seen how an LFSR followed by a phase shifter can be used to generate random patterns. So, if I apply these to the circuit under test, that takes care of the input patterns. But what about the output? See, the circuit under test will respond to these random patterns. Okay. I do not want to store these responses and try to figure out whether which is a good response. Is it a good response or faulty response? Okay. If I have to do that, then really I am not doing built-in self-test. Okay. So, we need a way. Okay, how do we see the output responses of this CUT, circuit under test, and decide whether it is good or bad, decide whether a fault has occurred or not. Okay. We really cannot afford to sort of look at the how a good circuit under test will simulate these random patterns, how will it respond to the random patterns, store the random responses and then compare. That is not possible. Okay, it beats the purpose. Okay. So, we need a clever way, right, which so that is where the signature register concept has been used. So, there is a signature register. So, what we do is we feed the outputs of the circuit under test to a signature register. So, the clock is common to all these three, the circuit under test, the LFSR and the signature register. We will initialize the LFSR with a seed and then we will start applying clock cycles. So, the CUT will get random patterns, okay, and the signature register sort of computes the signature of this cut. Okay, we will have to understand what a signature is. Okay. So, we can, what is meant by a signature? Of a circuit. Okay. Let us try to understand that. One way is this. Okay, I will show you the simple circuit. So, I will again take an LFSR. So, this is an LFSR, this is a shift register. So, I have taken a 3-bit LFSR. Okay. So, as you remember, in a 3-bit LFSR we sort of take the outputs of some of the flip flops in the shift register, take them through an XOR gate and feed it back. Now, here what we are going to do is we are going to take the circuit under test and the output of the circuit in the test and this feedback bit will be XOR. So, this is a single input signature register. Or SISR. So, let us understand how that works. Okay. So, assume that the flip flop has been initialized to 0 0 0, the shift register has been initialized to 0 0 0. Assume that the good circuit in the test, let us keep it very simple, let us say the circuit in the test is a AND gate. Okay, we will keep it very simple. And the random patterns I am applying are 1 1 1, 1 0 1, 0 1 1, 1 1 1, 0 1 1, 1 0 0. So, those are the random patterns which are coming in. So, this AND gate, a good AND gate will produce 1 0 0 1 0 1, sorry, this is also 0, right, 0 and so on. So, this is the output of the AND gate, a good AND gate. But suppose the AND gate has a stuck at one fault, it will produce 1 1 1 1 1. Okay. So, this is a output of a faulty gate which has a stuck at one fault. Alright. Let us simulate both of them. Okay. So, this is, let us say, the simulation of a good circuit and this is a simulation of a faulty circuit. So, initially both of them have 0 0 0. Now, when I do this one comes from a good AND gate. So, XOR of these two guys plus the 1 will enter here. Then the XOR of 0 0 and 0 will enter here. Then again XOR of 1 0 and 0 will enter here. Right. Then again we have XOR of 0 1 and this 1. So, a 0 will enter here and this 0 will cause 1 0 1 and the other 0 will cause 1 1 0. So, this is the final state of a good AND gate. Whereas, if the circuit had a stuck at fault and produces all ones like this, then let us simulate. In the first time, the one coming from the output of the gate will again cause 1 0 0. So, here there is no change, both of them will produce the same output, because this was 1 and this was also 1. In the next one, these two zeros and 1 will give you 1 1 0. So, you see the outputs have changed. Then again 1 has come from the output. So, 1 plus, so I will get a 0 1 1. So, here also it has changed. Once again a 1 comes. So, 1 plus 1 plus 1 is 1 1 0 1. Then 1 plus 1 plus 1 is 0. So, 0 1 0. And lastly again 1 plus 0 plus 1 is 0 0 0 1. Okay. So, you can see that their behaviors are very different. Okay. This the LFSR contents, okay, the content of, this is the content of the LFSR. is also content of LFSR. In this case, AND gate is good, has no fault. Here the AND gate has a stuck at one fault at output. So, if I take this AND gate and treat it as a circuit and a test, and apply this LFSR, okay, right, and if I am willing to look at the output of the LFSR as the true output, okay, I am not looking at the output of the AND gate at all. Okay, I am looking at what is the state of the LFSR. So, a good AND gate will leave behind 110, whereas a faulty one will leave behind 001. So, this is the signature of the AND gate. A good AND gate 110 is the signature of the, so sometimes we call it as a golden signature. So, the signature of the good circuit is the golden signature. What is signature? It is nothing but the content of the shift register after several clock cycles have elapsed. See here, if you allow only one clock cycle, unfortunately the signatures are the same, because the first bit is the same. Okay. If you only apply one clock cycle, then you have not been able to distinguish the good AND gate from the faulty AND gate. They both give the same signature. So, if you continue to test with many inputs, right, like in this example I have put 6 test vectors, then at the end if I look at the signature, a good circuit will have 110 as a signature, a bad one will have a 001. So, in other words, what I am saying is something like this. So, I can take the circuit and a test, I can have this LFSR followed by shift register. Okay. Some people will refer this to as PRPG or something like that, pseudo random pattern generator. Okay. So, I think this one, we have been calling it as an LFSR, but in the industry some people refer to it as PRPG or the pseudo random pattern generator. This is the phase shifter. There is a clock and the same clock also comes to your cut. If it is a sequential circuit, it will also need a clock, and then we will need a signature register. The signature register is also an LFSR. Okay. So, what we have illustrated in the previous example is a single input signature register, right. So, the testing is performed as follows: load seed in PRPG, apply and initialize this output signature register to all zeros. Okay. then apply some large number of clock cycles, that is the n cycles, compare the value in SR with golden signature. Okay. So, if the golden signature is different from the actual signature, we have a problem. Okay. Now, the golden signature, how do we store? Okay. We may know this golden signature from simulation. So, golden signature we obtain through simulation. We simulate the circuit, a good circuit, and figure out what is a good circuit signature. Whereas the actual signature, in the presence of maybe some faults, the circuit will provide, the hardware will provide. If they are same, then we have a reason to believe that the circuit is good. Okay. Same means circuit is okay, we could not detect any fault. Different means we have a cut is faulty. So, you see the responses of the cut, okay, we may have a lot of responses, but we have compressed them into a signature. Okay, this is called as compression. Okay, response compression, test response compression. So, in a big circuit, I may apply thousands of inputs, thousands of patterns. So, maybe we will apply 5,000 test patterns. And this may have 5,000 responses. But I am not going to store 5,000 responses. What I will do is I will store only the signature. The signature will be a small value. Suppose the signature register has a size of 16, right? Then it will only be 16 bits. So, that is why it is called response compression, and signature is a way of compressing the responses. Okay. See, if you have to go to the bank to withdraw money, right, how does the bank know it is you, right? Because the clerks will keep changing, right? The banking clerk who may provide you the money, the person at the counter may not have met you before, right? What they do instead is they store your signature. When you open an account in the bank, they will make you sign at least 2 or 3 times, right? And then when you present a check or when you do any other transaction, they will compare the stored signature with the actual signature. And if they are different, they will say there is something wrong. Okay, there may be a forgery here. Right. So, if the signatures match, they will issue the money. They will believe that you are the same person. In the same way, in the built-in self-test, okay, the PRPG is easy to build, the phase shifter is easy to build, and the signature register is also easy to build. All we have to do is we have to simulate the good circuit and find out the golden signature, and then have a way to compare the golden signature with the actual signature. Even that comparison you may be able to do. See, for example, if we know if the good signature or the golden signature is, let us say, 0 0 1 1 0 0 1, then we can actually do something like this. We can take an AND gate and say this is the good. Okay. So, if the signature is this good signature, this AND gate will produce a 1. Okay. If it is anything other than this good signature, the odd AND gate will produce so good or faulty bar. Okay. So, we can apply this this guy, okay, we can apply it here, okay, and the circuit will produce a single output saying I am good or I am faulty. It will test itself. So, that is the essential idea of built-in self-test. Okay. All right, when we come back, we will look at multiple input signature register. I have explained to you what a single input signature register is, right. I took the example of an AND gate, but we can do the same thing with multiple input signature register. Okay, so we will do that when we come back. So, welcome back. When we left off last time, we were talking about signature registers, and I had explained to you what a single input signature register looks like. So, today what we will do is we will sort of simulate that, right, in circuit verse, and we will see how it works. So, you will get a better clarity, right. So, let us go back to circuit verse. So, we will make a linear feedback shift register first using D flip flops. So, this is a D flip flop. Remember, it has a D input, it has a Q output, and it has 3 other inputs. One is called as the enable, the other is called as preset, and the third is called as asynchronous reset. Okay. So, we will take maybe 3 of these or 4 of these. All the enables will be connected. And this can be connected to logic 1 to say that these are always enabled. Similarly, the preset we do not want to use, so we can connect all the presets and we can connect that to ground. And all the resets will also be connected. And that is my reset input. So, here is my reset input. So, I label this as reset. All the clocks will be connected. Then we need to make it into a shift register, so we'll connect these guys together. You have to be careful not to short things. Okay. And then see, there is a short circuit, so you have to be really careful. Alright. Then there is a input, right? So the XOR gate will have to be added here. So the XOR gate is here. Right. Then if it is a simple LFSR, it will just, we'll connect it here. But now we are also trying to do an SISR, so we'll okay, and this will go here. And this input will have to come from the circuit under test. Okay, so we'll take an AND gate. Okay, and these are the inputs. So this is my circuit under test. This is my clock, or rather reset. And this is my clock. All right. So this is a good AND gate. Okay. So we were looking at the input to the AND gate is 1 0, right? And now we'll remove the reset and we'll apply a clock. Okay. So the circuit still remains in the 0 0 0 state. Okay. Now suppose the next input is 1 1. Okay. Then we apply. So you can see that this 1 has shifted. So initially we applied 1 0, then 1 1. Then let us again we apply 1 0, then 1 1. And then do one more time. Then 1 1. So I have applied 6 times 1011 1011 1011 1011. So it looks like at the end I have 0110. So this is my good signature. Okay. Now let me try to simulate a faulty gate by connecting this guy to a logic 1. Okay. Again we reset, then bring the reset to 0. Then we have to apply 6 times, right? So it doesn't matter. These inputs are not going to change anything here. So we applied 6 test vectors: 1, 2, 3, 4, 5, 6. Okay. So you can see that the output is something else, 1101. Okay. So earlier we had 0110, but now we have 1101. Okay. So this is an example of a single input signature register. Okay. So if it was a good circuit and the inputs are changing 1011 1011 every time, right? The output will be, let us do it again, 10, then 11, then 10, then 11, then 10, then 11. Okay. And 10, then last but not the least 1. So you can see that the outputs are different. The signature of the good and the faulty circuits are different, right? So that is why this is a signature register. Okay. Is it possible that somehow magically the signature of the good circuit and the faulty circuit end up being the same? Okay. So that is a question.